All right, simple harmonic motion is something we added to chapter 7. There's three examples given in the PAL assignments for simple harmonic motion: that of an object at the end of a spring displacing horizontally on a frictionless surface, that of an object at the end of a pendulum, so a long rod connected to a pivot on a ceiling, and that of an object attached to a spring displacing vertically, i.e., attached to a ceiling. The reason this is included in chapter 7 is that you can think of simple harmonic motion in terms of energy, conservation of energy. In each of these examples, you only have a restoring force present that you must have done some work to overcome to initiate the motion. From that point forward, all further motion is simply determined by the work done by the restoring force. Which then increases kinetic energy, which then, through conservation of momentum, serves to do work in overcoming the restoring force in an opposite direction, which builds up the potential energy of the same type and back and forth. So therefore, conservation of energy tells you that at any given time, if you know the change in potential energy between some previous point in time and that time, you can know the change in kinetic energy of your object. Some particulars about simple harmonic motion, independent of which picture we're looking at. You will achieve sinusoidal type dependencies between position, velocity, and acceleration versus time, and they are related to each other. And you can tell they're related to each other through the chapters 1 through 3 graphical kinematics relationships we've already established. So to start out with your position versus time, where everything here represents a position that's at the equilibrium position of whatever your system is. The equilibrium position is where there will be no net force acting on your oscillating object. For the objects on a spring, the left example, that's where the spring has not been distorted versus its equilibrium position. For the object on a pendulum, that's when the object is hanging straight down. And for the object hanging from the ceiling on a spring, that's when the object is at its rest position, meaning when you attach the object initially, gravity will act on the mass at the end of the spring, distort the spring somewhat, and then there will be an equilibrium position. That is the equilibrium position. If you then do some work to distort the springs or push the object on the pendulum away from the equilibrium position, you will begin an oscillation. If we give that oscillation a cosine function type for position versus time, so we're saying we're at equilibrium at time 0 there, it's kind of arbitrary where we start the clock, then you will have some velocity at time 0 here because you're in an oscillation and you will go in whichever direction you're going. In this case, we assume the positive direction. And as you're going, you will slow down until you come at a stop at some maximum amplitude. And we're going to calling that a value of A. So you can be at plus or minus A as your maximum bound positions. And this will proceed as a cosine function, and it will depend on time due to the fact that this is cyclical, which means it has a period, and a period is inversely proportional to a frequency. So we can write all of these things in terms of a frequency where 2 pi shows up in front, because 2 pi radians is the angular displacement achieved in one cycle. You can think of a cycle almost like a circle. It's when you start at one point going in a certain direction and you end back in that same point going that same direction. So cyclical oscillations can be described in terms of angular phases, where this would be 0 degrees, 90 degrees, 180, 270, 360. But here we're plotting it in terms of time. So the full time here is one period. Frequency is then the inverse of period, which is how many cycles you complete per unit time. All right, cool. So if this is what position versus time does, then we can just look at the graph to determine what velocity versus time does. And I'm going to have to fix the equations that I put on your quizzes, just a little tweak. There's a pluses and minuses that were in your textbook that when you analyze it, that's not how things work. At time 0, you have a positive slope. In fact, it's the biggest positive slope you'll ever have in a position versus time. So you must have a positive velocity. At a quarter of the period, your slope is 0. so your velocity at that time must be 0. At half period, you have a negative slope. That's the biggest negative slope you'll ever have, so you must be at the negative maximum value. At 3/4 of the period, you have 0 slope, and at the full period, you're back to having a positive slope in the original position. And there you go. You can, from that, infer the graph of velocity versus time. And what that is it looks like a sine function. It starts at a maximum, and 90 degrees later, it's at 0. So that would be a sine function with the same frequency. How do I know it has the same period? The wave reproduces in the same amount of time. And your textbook did a good job of working out how the amplitudes of these things relate to each other. So if you know the amplitude of your position versus time, which is just determined by how much you distorted the system in the beginning, then you can actually know the amplitude of the velocity versus time graph, which will relate to k, which is the force constant here. So that should have units of newtons per meter. It's how much force you build up per meter of displacement along the path, multiplied by the amplitude of the position versus time graph. So force constant, spring constant, the one you already learned about, is a type of force constant in a situation where the spring is the restoring force. You can also have a pendulum force constant, and even a force constant for the situation, the third situation, where you have a spring that's hanging vertically and you have both weight and spring force kind of involved here. In that case, the only thing changing is the spring force. All right. You can do the same thing to get acceleration versus time. You start off with a slope of 0 and the velocity versus time. So initially, your acceleration must be 0. Negative slope at 1/4, negative maximum value. 0 slope, 0 acceleration. Positive slope, maximum. Positive acceleration, maximum. 0 slope, 0. And we've completed, again, one wave. So the frequency here must also be the same. So everything inside the trig function stays the same. This doesn't look like exactly like a cosine or a sine function, but what it does look like is upside down, the position versus time graph. So this is a negative cosine function. And again, your textbook works out how the prefactors relate to each other, and this then just becomes a times k over m. And there you go. You can plot out at any given time what the acceleration versus time is. The other things your textbook worked out was that in any one of these cases, the period, which can go inside of your trig functions here, where the frequency is if you invert it, is 2 pi times the square root of m over k, where k is, again, your force constant. In the case of a pendulum, you could take it a step further, and you can actually put this in terms of the length of the pendulum and the gravitational constant, where the period of a pendulum oscillation is 2 pi times the square root of L over little g. I think that's pretty much everything you would need to get at any particular simple harmonic motion problem.